Welcome to the Explainer. You ever look at a page of really dense engineering notes and just feel completely lost? Well, today, we're taking this exact page on alternating current and we're going to translate it line by line into concepts that actually make sense. Let's decode these fundamentals together. Okay, so here's our game plan. First, we're going to learn the lingo, the language of AC waves. Then, we'll figure out how you actually measure its power. After that, we'll dig into some key relationships that are kind of like diagnostic tools. And finally, we'll put it all together and solve a real problem. And this question, this is really the heart of the whole thing. See, direct current, or DC, is easy. It's just a nice, steady, constant flow. But alternating current, it's always in motion, always swinging from positive to negative and back again. So how in the world do you put a number on something that just will not stand still? To answer that, we have to start with a vocabulary. Let's build up our understanding with the absolute basic building blocks of these AC waves. So, the most fundamental concept is the waveform. The simplest way to think about it, it's a picture of electricity over time. This graph literally shows us what the current or voltage is doing from one moment to the next. And here it is, drawn right there in the original notes, this beautiful, smooth, repeating curve. That's the classic sine wave. This is the ideal, perfect shape of the alternating current that's powering pretty much everything in your home right now. Every single waveform out there can be described using these four key things you see on the slide. You've got the cycle, the amplitude, the time period, and the frequency. Let's quickly break down what each one is. If we look back at the notes, you can see these ideas drawn out. A full cycle is just one complete pattern, one trip up and one trip down. And the amplitude, which you see labeled as VM or IM, that's simply the peak value. It's the highest point that wave ever reaches. Okay, so we understand the shape of the wave now, but how do we actually measure its power? How do we stick a single, useful number on this constantly changing value? Well, to solve this problem, engineers use two main measurements. The big one, the most important one, is the RMS, or root mean square value. Just think of this as the effective power. It's the AC value that gets the same amount of work done, like making a light bulb just as bright, as its DC equivalent. The other is the average value, which is exactly what it sounds like, but with a little trick, it's only averaged over half of the cycle. Now hold on, don't let all the math on this slide scare you. The notes show all this intense calculus to figure out the RMS value. And yeah, it looks really complicated, but the amazing thing is, it all gets simplified down to one very simple shortcut. And here it is. This is the magic number. The one thing you should remember from this whole section is 0.707. You don't need to do all that calculus. To find the effective or RMS value, you just take the peak value of the wave and multiply it by 0.707. That's it. Simple. And guess what? We see the exact same thing when we calculate the average value. Again, the notes show you the full mathematical proof. But just like before, it all boils down to another simple number you can multiply by. And for the average value, that magic number is 0.637. Just take the peak amplitude, multiply by 0.637, and you've got your average value over a half cycle. Two easy shortcuts for two really important measurements. Okay, so now we have our two key values, RMS and average. And this is where it gets really interesting, because the ratio between these values, it can tell us a whole lot about the actual shape of the waveform. So the notes introduce these two really powerful ratios, the form factor and the crest factor. You should think of these as quick diagnostic numbers. They tell an engineer about the quality and shape of an AC wave without even needing to look at the graph. We've cleaned up the formulas from the notes right here into this table. And here's the crucial part. For a perfect, pure sine wave, the form factor is always going to be 1.11, and the crest factor is always going to be 1.414. These numbers are like a unique fingerprint for a perfect sine wave. So why does this matter in the real world? Well, imagine an engineer is checking the power going into some really sensitive hospital equipment. If they measure the signal and the crest factor isn't 1.414, they know instantly that the power is distorted or noisy, and that could damage the machine. It's a super fast and powerful diagnostic check. All right, enough theory. Let's put all of these building blocks together and actually use them to solve a problem, one that's taken straight from the last page of these notes. Here's our challenge. We're given this one single compact equation that describes a voltage wave. Our job is to use everything we've just learned to pull out all its vital information: its peak voltage, its effective RMS voltage, its frequency, all of it. And the method for doing this is actually beautifully simple. It's really just a 4-step process. We take our equation, we compare it to the standard generic template for a sine wave, we match up the parts, and then we use our simple formulas to calculate everything else. And boom, here's the solution. Just by comparing the two equations, you can see the maximum voltage, Vm, has to be 200 volts. From there, we use our shortcut, multiply by 0.707, and we get the RMS voltage, 141.4. We can pull the other numbers right out of the equation and calculate the rest. You see how it all just neatly falls into place? So the big takeaway here is that once you understand the fundamental building blocks, a complex-looking equation like this, it stops being intimidating. It just becomes a simple, solvable puzzle. It's all about knowing the rules of the game. And there you have it. We started with a page of really dense handwritten notes, and we've decoded it into clear concepts and practical tools you can actually use. From the basic language of waves all the way to solving equations, you've now got the fundamentals down. But this leaves us with an even bigger question. The perfect sine wave we've been looking at today is the ideal, but it's just one pattern. What other invisible electrical shapes and rhythms are out there, powering all the technology that surrounds us? The tools we've learned today, they're your first step to understanding that entire hidden world.